Hi everyone, today you will learn on the linear programming model using graphical method. Let's start with the learning objective of this chapter. Hopefully, students will be able to understand the basic assumption and properties of linear programming. Graphical solve any LP problem that has only two variables by both the corner point and isoprofit line method. In this chapter, we have several subtopics. The first one is on the introduction, requirement of the linear programming problem, formulating LP problem, graphical solution, solving minimization problem, and for the next chapter, you will learn on the solving maximization problem. Okay, let's start with the introduction. Okay, many management decisions involve trying to make the most effective use of limited resource. For example, we have several resources, which is machinery, labor, money, time, warehouse space, raw material. So for the real world problem, sometimes we want to minimize the cost of the production, and also sometimes we want to minimize the time of production. Another objective could be we want to maximize the profit, okay, of the company. So all these resources we try to optimize the value with consideration with several constraints. So what is linear programming technique? Okay, linear programming technique is widely used mathematical modeling technique designed to help managers in planning and decision making relative to resource allocation. Linear programming technique is a long time ago, started around 1960 something. Okay, that the first problem that linear programming is produced at that time to solve a diet problem. That is the first problem which is used to be solved using linear programming technique. Belong to a broader field of mathematical programming. So linear programming is applied mathematics. Okay, applied mathematics, and we need some programming basic to come out with the solution. In this sense, programming refers to modeling and solving a problem mathematically. So LP has been applied in many areas over the past 50 years. It has four properties in common. The first one is all the problem in this world, we have two types of objective. Maybe we want to maximize a certain value, or we want to minimize certain quantity. So this objective we call as objective function in linear programming model. The second one is the presence of restriction or constraint that limit the degree to which we can pursue our objective. In the real world problem, we have objective, and also we have many variables to be considered. This variable we need to fulfill certain value. So this variable we can say, we can assume is known as the constraint in LP model. So there must be alternative courses of action to choose from. So course of action is the decision list that we at the end we can decide which one will be produced, which one will be considered. Okay. And the objective and constraint in problem must be expressed in terms of linear equation or inequality. So every equation in LP model must be linear, meaning that the x value is power of 1 and involve inequality symbol like larger, than, less than, at least, at most. Okay, so there is 4 property in LP model that we need to understand and consider. LP property and assumption. This is the conclusion from the previous slide. Okay, for the property of linear programming, we have one objective function, we have one or more than constraint, okay, we have alternative course of action, and we have objective function, and constraint must be linear. Okay, assumption in LP model, there are 5 assumptions. We have certainty, proportionality, additivity, divisibility, and non-negative variable. So we look at one by one. We assume condition of certainty exists and numbers in the objective and constraint are known with certainty and do not change during the period being studied. LP technique can be solved for deterministic problem or model. So the value of the variable must be known and not changes during the time. This we call as deterministic model. We assume proportionalities exist in the objective and constraint. And we also assume additivity, in that the total of all activity equal the sum of the individual activity. In the constraint, we can have additivity element where we add up all the value in the constraint. For example, 10 x1 plus 2 x3 plus 3 x3 must be larger than or equal to 20. So that is the additivity assumption. We assume divisibility, in that solution need not be whole number. So we assume that in the calculation of to get the final solution, the value can be in decimal, which is we can divide certain value with the some amount of value. All answer or variable are non-negative. This is very obvious. Okay, we have to remember that all the answer and all the value must be all positive or 0, cannot be negative value. Okay, formulating LP model. We have several steps in formulating the linear program involving the developing of mathematical model to represent the managerial problem. So there are several steps to formulate the linear programming model. The first one is completely understand the managerial problem being faced. Identify the objective and the constraint, whether we want to maximize or minimize certain value, and also understand what is the constraint involved. Define the decision variable, what is x1, x2, x3, and so on. use the decision variable to write mathematical expression for the objective function and the constraint. Then here in this chapter we will look at one of the problem that can be solved using LP technique, which is product mix problem. This product mix problem is very popular out there, where this problem usually faced by the manufacturing company. For example here, okay, in this chapter we will use graphical method to solve the product mix problem. And for your information, to use graphical method, the number of variable involved is only 2, okay, which will represent the x and the y. Okay, so this technique is a very basic one, okay, where we try to solve using graphical method for 2 number of variable. 2 or more products are produced using limited resources such as personnel, machine and raw material. But for the constraint, we can have more than 2 constraints. The profit that the firm seeks to maximize is based on the profit contribution per unit of each product. So usually in product mix problem, we try to maximize the profit of each product. The company would like to determine how many units of each product should be produced so as to maximize overall profit given its limited resources. So this is the objective of the company. They want to maximize the profit given the limited number of resources. So they want to know how much product of X1 should be produced and also how much product of X2 should be produced in order to maximize the profit. Okay, so now we look at the first maximization problem for LP. Okay, we have one type of problem example here. The Flair Furniture Company produced inexpensive table and chair. So this company produced table and chair. Okay, we only consider 2 types of product from this company, which is X1 for table and X2 for chairs. Processes are similar in that both required a certain amount of hours of carpentry work and in the painting and varnishing department. So there are 2 activities to be that involved in the making of table and chair. Each table takes 4 hours of carpentry and 2 of painting and varnishing, while each chair requires 3 hours of carpentry and 1 hour of painting and varnishing. So the total number of carpentry time is 240 hours and the hours for painting and varnishing is 100 hours. So that is the total of resources available. Each table yield a profit of $70, and each chair have profit of $50. So in this information, we have several points that we know that the objective is to maximize the profit, and the profit for table is 70 if the company produce 1 table, meaning that the company will gain $70. For the chair, if the company able to produce one chair, so meaning that the company will get $50 profit. Okay, the total number of carpentry hour and also the painting hour is given 240 and 100 hours. So we arrange all the information in the table like this. Okay, we have carpentry, painting and varnishing, and also we have the profit. Okay, for the column represent our product, table and chair, which is we use the symbol T and C, and this is the total of available hours for the constraint. So carpentry, okay, table need 4 hours for carpentry and chair need 3 hours for carpentry, and the total number of hours for carpentry is 240. The same thing for painting and varnishing. And this is the profit for each table and chair produced. Okay, so the objective is to maximize the profit. So now you will learn on how to build the LP model. Okay, you have to know that the objective of the study, whether we want to maximize or minimize. So in this case, we want to maximize the profit, and the constraint involved is the hours of carpentry time used cannot exceed 240 hours per week. So we have to understand that the total number of carpentry time for both products must be equal to 240 or less than 240. Cannot be more than 240. So the symbol used in this case for the first constraint is less and equal. For the second constraint, painting and varnishing time cannot exceed more than 100 hours per week. So the decision variable in this problem represent the number of table and the number of chairs to be produced per week. Okay, so we have the symbol T and C. So let's build the LP model. Okay, which contain the value and the symbol. Okay, so this is the perfect return of objective function. Maximize profit Z value, okay, which represent the Z, symbol Z for the objective function, equal to $70 profit for table and $50 profit for chairs. Okay, this is how we write the objective function of in LP model. Okay, to develop mathematical model relationship for the two constraints, we have the first constraint is about carpentry, where 4 hours per table of 4 hours carpentry of a table plus 3 hours carpentry of chairs. So we can write like this: must be less and equal to 240. This is the maximum number of resources available. Okay, this is our first constraint. Second constraint is 2 hours for painting and varnishing of table, of making a table, and 1 hour of painting and varnishing for making a chair must be less than equal to 100 hours per week. So this means that each table produced require 2 hours of painting and varnishing time. So both of these constraints restrict production capacity and affect the total profit. Okay, so the assumption of LP model, still remember that just now I mentioned about the assumption of non-negative. So we have to make sure that the total number produced of table and chair must be larger or equal to 0, cannot be negative value. Okay, so this is the complete LP model that we can represent in our solution, where our objective is to maximize the profit Z equal to $70 T plus $50 C, subject to is referred to the constraint. So we have 40 plus 3C less than equal to 240, 2T plus 1C less than equal to 100, and we have non-negative assumption, which is T and C must be produced for the amount of 0 or positive value. Okay, so X represent for C, T represent for Y, but this is for the constraint. Okay, so table is for X axis, chair is for Y axis. So in this case 0 and 80, and for the Y axis we assume we produce no chair, so we get 60 and 0. Okay, so we can plot one point here. Okay, so 0 and 60 and 0 and 80. Okay, so we have one line. Okay, graph. Okay, here if we produce 0 number of chair, and then the total number of table that can be produced is 60. And if our decision here is we produce 0 table, so meaning that we can produce 80 number of chairs. Okay, so let's go to the okay, here we have to determine the value. Okay, we have to determine the feasible region for the first constraint. Okay, any point on or below the constraint plot will not violate the restriction. Okay, this sentence meaning that okay, this is our maximum okay number of production for table and chair, and if we produce less than this maximum number, so our solution is acceptable. We call as feasible solution, but the problem is our profit is not fully optimized or minimized or maximized. So if we decide to produce 30 table and 20 chairs, our profit here is less than compared to this solution. Okay, so remember that our target is we want to produce maximum number of chair and table that will give you maximum profit. Okay, any point above the plot will violate the restriction. Okay, if we choose the solution which is larger than this constraint line, so meaning that our solution is infeasible, which is not acceptable. Okay, because we already crossed the limited resource of carpentry time, which is 240. So if we produce 70 table and 40 chair, meaning that our carpentry time is above 240. So the solution is not acceptable, cannot be accepted, and we can say this is infeasible solution, this is feasible solution, and this one is feasible solution. Okay, so this is how they show you okay the total number of constraint. If we produce 30 table, 40 chair, we got 240. So this is the maximum number of resources allocated for the carpentry hour. Okay, but if we only produce 30 table and 20 chair, we just use 180 hours of carpentry. But if we produce 70 table and 40 chairs, so actually we use more than the maximum number of carpentry hour, which is 400. Okay, alright, that is the first constraint. Now we plot for the second constraint. So for the second constraint, okay, we assume we produce 0 number of chair, then we got 50 number of table. If we produce 0 number of table, we got 100 chairs for the painting and varnishing constraint equation. So each constraint must be drawn in this graph. Okay, so now for the blue color region, this is the feasible region. Any solution in this area is acceptable, but the solution above this area is unacceptable. This one is we call as infeasible solution. Okay, so to produce table and chair, both department must be used. We need to find a solution that satisfies both constraints simultaneously. So a new graph shows both constraint plot. Okay, the feasible region or area of feasible solution is where all constraints are satisfied. So any point inside this region is feasible solution, and any point outside that region is we call as infeasible region. So just now we have two constraints. We have to combine all these two constraint line in one paragraph. So we can see here the feasible region. We have to understand where is the feasible region, which is the combination of these two lines. Okay, this one is not feasible region because this constraint is not fulfilled. Okay, the same thing for this one. But for this region, both constraints fulfilled. Okay, so any solution fall in this region is acceptable. Okay. Okay, we try to see this point. If we have 30-20, so we choose to produce 30 table and 20 chair. So we can try to put this value, okay, in our constraint equation. So this show that the constraint number 1 and number 2 is fulfilled, because less than 240 and less than 100. But for this point is 400 and 180, so this point is called infeasible solution because they already exceed the number of 240 for carpentry hours and also 100 for painting hours. So this solution cannot be accepted. Okay, and for this solution 50 and 5, okay, we try to test whether this solution is in feasible region or not. Then we can see here, okay, for the first constraint is fulfilled because less than 240, but for the second constraint cannot be accepted because larger than 100 hours available per week. Okay, the first step is starting with a small but possible profit value. We graph the objective function. Now we want to assume small number of profit. Okay, so we assume that a small number of profit is $2,100. So $2,100 equal to 70. This is the equation for objective function. 70 profit for table and 50 profit for chairs. So solving for the intercept, we can draw the graph. Okay, so this is obviously not the best possible solution. Yes, this is not the best possible solution. Further graph can be created using larger profit. So the further we move from the origin, the larger the profit we will get. Okay, so the highest profit 4,100 will be generated when the ISO profit line pass through the point 3040. Okay, here they already mentioned that the maximum profit can be gained is 4,100 and the optimal solution is 30 and 40. Okay, for this problem. Okay, now how we want to get this optimal solution. So let's draw this one. Okay, based on this equation, the objective function equation, we assume that our value of profit is the small one, 2,100. So we draw the line. Okay, we assume here there is 0 number of chairs, so we got T is 30, and if we produce 0 number of T, okay, we got C is equal to 42. Okay, so we have two coordinates here and draw the line, and now we want to move using the ruler, your ruler. Okay, move a little bit, okay, above until you reach the maximum touch, okay, of the region, visible region line. So let's see here, you move by the ruler. Okay, actually to solve graphical problem, you need to have graph paper. Okay, you have to need graph paper, and you need to draw the graph perfectly. Okay, you need to draw with the right scale. Okay, so that if you move using the ruler, okay, from here to here, here to here, then you will see the last touch of the visible region line is here. Okay, so the purple color is the last touch of the visible region area. Okay, so that is the optimal solution to the problem of Flair Furniture company. Okay, so you already learned on the method of ISO profit line solution. Okay, so let's stop here. Okay, on next class you will learn on the second technique of graphical method, which is corner point technique. Okay, so that's all.